There are a lot of domain-specific solutions for these problems, like neural style transfer or image colorization models, or even like elementary problems can be considered as a image-to-image translation, like edge detection or applying filter or blurring or all that. So these are some examples: colorization, segmentation, uh, cityscape to segmented image, style transfer, background removal. So like it's basically very general problem. So the question is, there is always a, we have to always find a map from an input domain X to an output domain Y. That is, we want to find a function G from X to Y that satisfy our training data. Can we build a general purpose solution to this problem? Yes, we can. We can use class of machine learning models known as GANs. So there's a quick recap for generative adversarial networks. So GANs are form of generative models which learn via an adversarial process. They were introduced in 2014 by Ian Goodfellow and all. Uh, GANs consist of two submodels, a generator G and a discriminator D. So the goal for generator G is to map from some random noise to a domain X. And the goal for generator D is to get the probability that the sample it got as input was generated by G, or was it an actual training data sample. So it returns 1 if it was a training data sample, and it tries to return 0 if it was a generated sample or a fake sample. So the canonical example used to describe was, think of G as a fraud trying to create fake currency and use it without detection. And think of D as working for the police who is trying to detect counterfeit money. So G tries to generate fake money, and D gets input as both real money and fake money and tries to determine the probability that it's real. So mathematically, the objective for D is, if a sample X came from the training set, we want to predict 1. So that's the same as maximizing this expectation. The log is there for just computational reason. We want to maximize G of X. And similarly, if a sample GZ was generated by G, then D needs to predict 0, or just 1 minus DGZ. If we maximize this, if we maximize both these terms simultaneously, that becomes the objective for D. So, but the objective for generator D is the opposite of G. It wants to fool D into thinking that the sample is an actual sample. So basically, G tries to minimize this same expectation. So we can combine it all as an objective, where there is an expectation of D of X and another on 1 minus D G of Z, where the discriminator D tries to maximize this function and the generator G tries to minimize it. Note that the generator G doesn't have effect on this function. This is just a 2-player minimax game. There exists a straightforward extension to this previous generators called conditional GANs, where we pass a conditional random vector to both G and D. Not random, but a vector to both G and D. Basically, D also accepts another argument, and G also accepts another argument. Okay, so that was the background. Supervised image-to-image translation. So in supervised image-to-image translation, there always exist paired samples. Like this is an input sample and output sample. This is another sample, input, output. There always exist pairs. The question becomes, why bother with GANs at all? Can't we use a simple CNN generative model for the image-to-image problem? Like in UNet, we can just using a normal CNN, or there are also other models like encoder decoder. So why don't we use them? Basically, CNNs learn to minimize a loss function. The learning process is automatic, but we still need to choose a loss function. We need to basically tell what CNN what we want to minimize. The problem with that is if we take a naive approach and just tell the CNN to minimize the L2 norm or the Euclidean distance between input and output image, it will try to get blurry results. The most common reason for that is it is much safer for the generator to predict a blur image because the L2 norm tries to predict the mean of the distribution. Because there is a lot of just a textured image, a lot less edges. There is not much. If we predict a mean pixel between two edges, then we are getting a we the L2 loss will basically try to minimize that, but that will result in a blurry average image. So the pix-to-pix paper is was introduced. Basically, we want to specify the generator that make the output indistinguishable from the reality. So that's a very big statement, but this is what exactly GANs do. Basically, GANs try to generate a probability distribution, try to sample from a probability distribution that the discriminator thinks came from the real distribution. So the pix-to-pix model is based on a conditional generative adversarial network. It was introduced in 2017. It was one of the first general purpose solution to the image-to-image translation network. So let's change that. Let's change the normal GANs. Normal GANs try to generate an image based on some random vector, but we don't want a random image. We want something that corresponds to an input-output pair. So we pass the input image as a conditional matrix to the GANs. That becomes a conditional GAN. And also in their experiments, they found that using both the adversarial loss and the normal standard losses like L2 or L1, they used L1 loss, combining them results the best looking results, gives the best looking results. So the loss function for the D is unchanged. Just we are not, yeah, the loss function for D is unchanged, but G has now also tries to minimize the L1 loss just to do some extra work. So the adversarial loss for the conditional GAN is this, but there is also an L1 loss for generator G. If we combine these both, we basically want to find the generator. So that's a combination, and we take a weighted combination. There is an extra hyperparameter lambda that is experimentally set. So in most of their data sets, they set a lambda of 100. Now let's build the discriminator for the GAN. Since we are already using a traditional loss like L1, uh, we are already sort of minimizing the low frequency data. We are predicting low frequency data. They can produce the blurry results, but we just need to make sure that the GAN also predicts the high frequency data. So that's the main idea behind their specialized discriminator PatchGAN. So what PatchGAN does is model only the high frequency structure in the generated image. To model this, they restrict their attention of the PatchGAN to a image patch. Rather than predicting 0 or 1 for the whole image, they predict a matrix k by k which correspond to a patch of the image. So one advantage of PatchGAN is that the discriminator can scale very well. So if we increase the resolution, we can still get a discriminator architecture that predicts the probability that a small patch was in the actual data. But the resulting matrix would be a larger matrix, not k by k. If the resolution is higher, we will get a larger k by k matrix. So there's a small visualization for PatchGAN how it works. Uh, so there was a small confusion, like the PatchGAN doesn't literally breaks the image into patches and passes through the generator. It just simply applies a CNN to the generator and result stops at a k by k matrix rather than going all the way and predicting a 0 and 1 value. So basically each each entry in the k by k matrix correspond to a receptive field, not exactly a patch, because between pixel there is some overlap. Between pixel there's some overlap between the original image and the result between fake and real. uh, yeah, that's it. And the architecture was inspired by the DC can paper. Instead of convolution pooling layers and all that, they used blocks of the form convolution, Bashnom and ReLU. So they used Bashnom instead of pooling layers, and we downsample the image up, till we reached a k by k matrix. So for the generator, one of the obvious choices is the encoder-decoder network. In the encoder-decoder network, the input image is passed through a series of layers or blocks, like we seen previously, convolution, Bashnom, and ReLU, till we reach the a size one by one and some number of filters, specifically 512 here, called the bottleneck. After that, the process is reversed until we reach the resolution of the original image. This is called the decoder part of the network. Also note that in all the generators that we will see in this presentation, we don't pass an extra noise vector z like we do in the original GANs. The noise is introduced just by via dropout. We use dropout both in training and test phase of the model. So there is just a visualization of the encoder-decoder network. We downsample until we reach a bottleneck, and then we upsample. That's the generated image. For the decoder part, we use transpose convolution or fractionally strided convolutions. That's from a ReLU. For the encoder part, instead of ReLU, we use leaky ReLUs. Now, there's a problem with the encoder-decoder network. For a lot of image translation problems, there is a lot of like low-level information shared between input and output image. For example, in the case of colorization, the input and output share the location of edges. We don't want to lose this information like we do in the encoder-decoder network. We don't actually lose, just it's not very efficient way to pass the information. So to preserve this information, we add skip connection to create a unit-like architecture. So by skip connection means this is the normal encoder decoder. Here are the modules. In the unit variant of the generator, we add skip connection to the encoder and the corresponding decoder layer. So for data sets for the Pix2Pix model, I used like 3 data sets. One of them was satellite to map. It has about 1,000 images from the original paper Pix2Pix. They uploaded that on their website. Trained for about 150 epochs with batch size 1, and also an edges to shoes dataset with about 50K images. Trained for 30 epochs, batch size 1. And also an extra dataset I found on Kaggle. This is a colorization task. 14K images, 4K validation images, trained for about 75 bucks, batch size 1. All of them basically took me about a day to train. Some extra details. Optimizer,
So is
we
there
use
a
Atom. Yes, ma'am.
sorry, Gurdit. Is there a reason why you preferred batch size one for all of them?
Yeah, they in the paper they mentioned batch size 1. Actually, I tried with batch size 32. It was very fast, but the resulting images were not that great. So I'm not sure if there is a theoretical justification for that. Maybe there's a lot of uh, local minimum variation between that. I don't
Okay,
know exactly, but they found
okay,
that batch size 1 worked great for all of that.
okay, okay.
Uh,
All right.
for the optimizer, we use Atom with these hyperparameters. These are all the same hyperparameters they used in the paper. Also, for the generators and discriminator I mentioned previously, I actually used a somewhat modified version of them, which we will see in the later section. Okay, so these are some of the results. This is the input image. This is the output image that we are trying to generate, and this is the predicted image by my GAN. So we can see that it's a little bit wobbly lines between the roads, but it gives good results. So some other examples. So even though we can see there is green here and tries to get it green, but there is no green in the actual Google Maps. So this data set was scraped from Google Maps, aerial and normal images by them. And small. Okay, so
So
some
this
bad
is
case.
these examples you're showing for filling, is it?
No, this is just the input image, and it tries to generate this image from the input image. And this is the output pair that we. This is valid from validation set, not from training set. This is the output image that it
So
generates.
the output image is the street map that we see, is it?
Yes, ma'am. That is what we're trying to do.
That's
We
what
can
you're
go
trying
also.
to create.
Yes, ma'am. We can also go the other way, but I didn't do that. Since we have a
No,
paired
no.
data,
So
we can
no,
go
I'm
either.
just trying to understand what is it that this thing is trying to create.
Okay. So,
From the given image, it is trying to
mhm.
create the street map because you have input and given these sets of inputs and outputs.
Yes, ma'am. These are the paired examples,
Huh.
and this
Okay,
is
okay,
the domain X and Y, and we are trying to map X to Y.
okay, okay. Thanks.
Okay. So some bad cases where this fails. So it generalize well to grassy areas. I looked in the data sets and there were very few samples of roads in the grassy area. So that's probably why. And also there is a highway there actually. I don't think even humans can see that, and it doesn't follow that. Uh, Another bad case. It should have generated a highway here. It didn't. So highways are like not that frequent in the data set. And also we can see that there are a lot of grassy areas. We would expect something like a grass green to be here, but in the labeled image there is not. So that's why it fails.
But then the predicted image is giving you the correct result right?
Yeah,
For the grassy area.
yeah.
Okay.
So the next data set, there are basically a paired image samples of sketches. Basically, I think they just did edge detection, and the output image is shoes. I think they scraped this data from Amazon. I'm not entirely sure. Uh, and this is the predicted image that my model generates. This is one of the samples. This is
So
another
here I
sample.
have a this was exactly what my question was going to be. Is that how does
Mhm.
it know which colors to put in?
Yeah,
Because you
it
will have
doesn't
lots
actually.
of
Mhm.
yeah. Okay. Now in
Yeah,
the first
I
image,
think.
it seemed like,
Yeah. It's very good.
but this is an
That's
actual
just
pair of
coincidence.
input output image. So you're
Mhm.
so
I think that's just coincidence. We will see later in the colorization section that it generates different colors for the
okay.
input image. Uh, I think most of the shoes that look like this has a very brown, muddy color, so it generates this, and for this it generates this, and it generates a for the sketch colorization. There are input and output pairs, which is basically line sketch and the colorized sketch. So we can see that the colors it generates are not exactly the same, but it's a pretty good result. I don't know what happened here, but uh, yeah. And some bad cases. Okay, so sometimes it will generate different colors for the eyes. So it doesn't exactly remember what color is generated in the left eye or in the right eye. So it will do some things like that. So now for the unsupervised problem. The unsupervised image-to-image translation, we basically have two sets of images. Rather than paired example, we have set X and a set Y. Maybe because either we didn't label them or because labeling is not exactly possible. Like we will see in the style transfer problem, we pass an landscape image and a image painted by some artist, and we will try to model from X to Y. Uh, since we don't have exactly paired images because they don't exist, we will try to use this unsupervised learning settings. And even in this horse and zebra example, we won't exactly find a zebra standing in this exact pose. So paired examples are not possible. So we saw how we can use conditional GANs to tackle the supervised problem. Surprisingly, we can also extend the previous approach to work in the unsupervised setting. So this method was proposed in the Cycle GAN paper in 2017. Uh, it basically builds up two GANs, uh, capturing transformation between both domain X and domain Y, G and H. And this model is a cycle consistency loss. So basically, the issue with just using GANs is that it sometimes generates only one sample for the Y domain. It doesn't really know. Uh, so, for example, if I say a generator G has a discriminator dy in this domain, and the generator G always predicts this same zebra, the discriminator will think, oh yeah, this is in the this domain. So, but that's not what we want. We want a zebra in this exact pose. So what we do is add a cycle consistency loss. So cycle consistency loss is basically just a reprojection error. We take two images from domain X and Y, and we apply both G and F sequentially. So basically, intuitively, what we want is if we go map a horse to a zebra and map that zebra back to a horse, that resulting image should approximately be equal to the original image. So we do that for both the generator. We take k from x, map it to y, and then map it back again to x, and we want them to be approximately similar. We introduce this equation as a loss. So also for the other generator. So this is a visual representation. So what we do is take X, pass through the generator GY, it generates a fake image. We also don't remove the adversarial loss. Obviously, it's there. So the adversarial loss for the domain Y discriminator for the Y domain will also produce a loss, and we map it back, and we take some loss between X and the X cycle, the reprojected image. So the adversarial loss for both the generators are for both the models are this, uh, a combination of this, and the cycle consistency loss is just L1 norm. Uh, they didn't take L2 norm. I don't think they gave any justification to why, but it's just L1 norm. Uh, and the full objective then becomes adversarial loss plus cycle consistency loss. So for both the cans, we have adversarial loss and we have a cycle consistency loss that we add through a weight. And this lambda is about 10, I think, for all the datasets. Now, the discriminator architecture for the cycle gun model is mostly the same as Pix2Pix model, but there are a few changes. We replace batch norm with instance norm, which works good for style transfer task as found in this paper. And also, we replace the negative log likelihood objective by a least squares loss, which is more stable and generate higher quality images, uh, which was described in this paper. So instead of like passing through log, we take a mean squared error. Yeah, for both generator and discriminator. So for the generator for cycle gun, we have a completely new architecture which was inspired by networks in this paper. Basically, we build the generator in forms of modules of convolution, instance norm instead of batch norm, and ReLU. But now we have a 3 convolution layer. Then we have several residual blocks. To be specific, in the case of 256 by 256 images, we have 9 residual blocks. And then we have some convolution to sample up, and finally a convolution to map to RGB or whatever number of channels you want. So in the case of colorization, in the previous section, I just did RGB to RGB, but that's not exactly what's done in all of the papers in the colorization task. They take RGB image and convert that to LAB sample space, and then just try to predict A and B sample space, or the color part, hue part of the image, and take L from the input image. But I just did it normally, pass the whole image to and produced an image. We can have any as much channels as we want. For the cycle GAN, the data sets used, I just did only one data set, because this model is like very heavy to train. You're basically training two GANs simultaneously. Uh, it's at least twice the number of hours to train the pix-to-pix model, but also more because each of the GANs learn from other. So there's an issue there. I just trained it for 10 epochs, took me like a day with patch size 1. Uh, Optimizer and learning rate are same, but the lambda is different. Lambda is
Sorry, how
10
many
here.
images did you? How so, I've missed. How
For
many
the
images did
horse
you
to
train?
zebra, I think that was about 1,000 images, I think. Sorry, I did not mention
Okay.
that here. 1,000, I think 1,300 and 1,000 X and Y. Uh, yeah, and about 400, I think, validation images. That was about it, I think.
Okay.
Yeah, and some outputs. So these are input images. So as I did not train for that many epochs, they trained for about 200 epochs. So I did not have the time to do that. So I just trained for 10 epochs. I got okay-ish results. So for the input image, these are horses, and it tries to go to the zebras. And also, since we trained another generator simultaneously, we can also go from zebras to horses. You can see that the results are not that great because it's still predicting stripes here. It should not. But that's what I got about
Also, in the
for
previous
10
image, it
epochs.
sort of missed the.
Mhm.
Only the legs are visible. The head, not for the story.
For which image? This one.
The younger one has no head
Yeah.
in the zebra.
Yeah. I think, yeah,
So yeah.
and some also bad cases. Uh, so this problem is generally one of the problems of the whole model. Uh, we It cannot like really change the shape of the input image. So it what it tries to do is kind of like retexturing the image. Uh, that's one of the main drawbacks of these models. So we can see here it tries to generate a zebra here. I don't know why. I think maybe because there's a brown color here. So and failure case for zebra to horse look like this. It doesn't basically change the zebra. So I think that's because the stripe size are very different here, and the model is not like scaling invariant. So that's what's happening. Maybe better generators would produce good results. So uh, yeah, that's about it, I think. uh, for the source code, I have uploaded that on my GitHub if someone wants to look, and references. Do I have time to go through the source code? Yeah, I
Yeah,
think
there
so.
is time.
Okay. Basically, what I defined was a general convolution block, which is basically a sequence of convolution and an instance storm and an activation and maybe a dropout. For the encoder block, we add a convolution block which goes down, has an activation of leaky, kernel size 4, and a stridist of 2 to downsample the image. Uh, and for the decoder block, we have a normal convolution block which goes up, basically transpose convolution. Activation is ReLU, and we also use dropout here. And for the patch discriminator that we use in both the models, we have a initial block which is just convolution ReLU. We don't use an instance from here. That was mentioned in the paper. And also, there's a specific thing about it, like there's a conditional flag. So we use patch discriminator in both unconditional and conditional setting. So when it's conditional, we pass the paired example stacked on the number of channels. So we take net channels, like if the number of channels was 3, the input channels is 6, because we pass the input example and the generated or the actual to the discriminator. And we pass it through some convolutions, encoder blocks, and at the end we pass it through a convolution to get the number of channels to be 1. uh, and we also pass it through a sigmoid to get the matrix in range 0 comma 1. So for forward, we can see if it's conditional, we concatenate it on dimension 1, basically number of channels x and y, and pass it through the model. And except unconditional, we just pass the input. So for the unit generator, I have several encoder layers. I've defined this generator, but I have not used this. I've just used the generator defined for the cycle time paper. For the encoder layers, similarly, we don't use a instance DOM here. Add some encoder blocks, some decoder blocks, pass it through TANS, because the images are actually in the range of -1 to 1. I did some image transformation. Uh, yeah. I resized it to 56 by 256 and normalized it with this mean and standard deviation. So the image is in the range -1 to 1. That's why I pass it through -1 to 1 for the generator. For this, for these skip connections in the unit model, I basically add the activation of the encoder to the discriminator. I basically get the index of the corresponding encoder activation, add it to the uh, activation for the decoder, and pass it through. So that was the unit generator. For the ResNet generator, I have defined this ResNet block. So ResNet block is basically a couple of convolutions, but at the end, we sum the input to the output. Basically, add a skip connection between blocks. For the ResNet generator is similar. We add some convolution layers and some residual layers, which is about 9 for 256 by 256, and some decoder layers, and pass it through TANH to get in the range -1 to 1. Yeah, that was about the networks. And for the fixed model, I think I can just show the loss function. And also I did float 16 training instead of the usual to improve runtime performance, like decrease time. So for the loss, yeah, am I audible right?
Yes, we can hear you.
Hello? Okay. I don't think I can hear you. So, sorry. Uh, for the
Yeah, I can
discriminator.
hear you. I'm able to hear you.
Oh, okay, okay. So for the discriminator, we are trying to take a discriminator here. So we take two samples from the data set X and Y. These are paired samples. Pass it through the discriminator. It's a conditional discriminator, so it takes both, and it generates some probability matrix. For the real image, we want it to predict 1. So we pass a one matrix of same size as the KYK matrix, and for the loss we have used like mean squared error loss, or we can also use cross interpret. And for the fake part of the generator, we predict a fake image, pass it to predict 0. So we set the loss to 0 matrix and the discriminator. And we train the discriminator. For the generator, we would try to predict the opposite of the generator. For the fake image, we would like the generator to predict 1. So we train the generator to predict an image, something that the T will predict 1. For the L1 loss, we multiply and add it that. And yeah, that was about the apex to pix. And cycle can is, I think, very similar. So we train the generator. We train both discriminator and generator together in this case. So it's a bit more computationally intensive, but the main idea is about the same. Yeah, I think that was about it. Any questions?
Yeah, so one of these questions that I asked before, and I'm still
Mhm.
intrigued about it, is the batch size one. And so that's one thing. The another
Which
thing,
question? Sorry,
another
I
thing,
didn't get you.
why is the batch size chosen as one, which is
Batch size,
predicted?
yeah.
I mean, one you,
I don't
yeah,
think they gave a very intuitive justification as to why that was chosen on.
yeah,
They
yeah.
just
You
said it.
you said that, yeah, yeah. You. So I'm just saying that that is the only one question that I have, and I'm intrigued by the choice. I don't. I mean, I've never seen actually batch size one being chosen. So if
Mhm.
anybody else also here has some something, some light to shed over it, they can please do so.
Okay, so like in one specific case, they choose the batch size to be four. So, but that was in the case of like they had about 150,000 images. So I think that was just to speed up the computation, and one
Yeah,
would
so
have maybe
the
performed
only
better.
time I have seen small batch sizes is if you want to, find out after a few epochs how it's going.
Mhm.
Uh, but this peculiar choice of batch size one everywhere, that is intriguing, what I think.
Yeah, yeah. I don't think there's a justification. Batch size has one day term it instance normalization for some reason. Has demonstrated to be effective at image generation tasks, but they don't give like a reasonable justification.
Okay, there's some reference there. I'll look it up. 54 they say.
Okay, so it's instance normalization paper.
Okay. Okay, at least that is something to look. I'll look.